All right, today we're going to learn about some transformations of different types of functions. The types of functions we're going to transform are the linear function, the absolute value function, the quadratic function, and then they mention this constant function, which is linear, but it's just a horizontal line. So we're very familiar with what a linear function looks like. And a quadratic function, that's your parabola. And just in case you don't remember what an absolute value guy looks like, you may have not seen that before. Remember the bars? It looks like a V. And all of these guys that I have right here are the parent functions. In my classroom, you'll see them hanging on the wall that I have all those different graphs. But as you can see, the first guy right here is just your linear function. He's not horizontal line, so he's going to be oblique or even vertical. It's a linear situation. So then the second guy, do you see how it makes that V-type shape? That will be your absolute value. So we're just recognizing these guys. I know I'm moving fast for you, but you can pause the video to write this stuff down. The absolute value, I'll let you abbreviate it like this. And you can see Mr. Curvy guy right here, he's not the V and he's definitely not a line. He is your quadratic function. I do understand if you accidentally wanted to put parabola, because that's what shape this is, but that type of function it is quadratic. So I kind of mowed through the first three for you. Why don't you try to do that on the last three right here? So give the video a quick pause and we'll see how we do. Okay, this guy is an absolute value due to the fact that he's a V-type shape, and a constant function due to the fact that even though it is a line, right, it is a horizontal line, so they're calling that constant. Because y is constantly 3, like 3, 3, 3. The y value of every single one of these points is 3 in this guy, so that's why they call it constant. And then this is just irregular or linear because he is oblique. So what we're going to do is we're going to see how these graphs move around, a transformation. First thing is I want to kind of make sure that you understand what it means when something has been reflected over the x-axis, just as a visual. Like this dude right here is your parent quadratic function, your plain Jane parabola. Like if this was an ice cream flavor, he would be vanilla. But remember, of course, this is the x-axis. If I want to reflect him over the x-axis, he's going to come down here, which basically looks like this dude that I have. And what did that was this little negative symbol right in front of it. We'll learn a little bit more about that later. And the same thing happens if you had your absolute value. This is a plain Jane absolute value guy. If it was ice cream, it'd be vanilla. It's very plain. If you wanted to reflect him over the x-axis, do you see how there's a little minus out in front of that? All right, so it's time to dive in, and I hope that we have in front of us the purple note card also. Your teacher should have given you the purple note card. The purple note card, yes, you get to use this on your tests and quizzes right here. It is a 4-step process to ask you some questions of how this graph that has been provided for us has changed from the parent function. Well, our very first thing to do is to recognize who is the parent function. Is this like a line? Is this a parabola? Or is it an absolute value guy? Like it's got some flavoring to it now. It's not a plain Jane vanilla ice cream. It's got this in there and this in there. Those are different than before. So the parent function I want to recognize before. So we'll write the word parent with a colon next to it. Do you see how it's got the absolute value bars? The parent function of this guy is y equals the absolute value of x. So this is what it looked like before they added all the flavoring. This is the vanilla ice cream, then they added some stuff. What kind of flavoring did they add? Well, check it out. I've got on your purple note card this very generic formula that's got some A value, B value, an H value, and a K value right here. And I know that these are parentheses. They're just a grouping symbol. In our particular case right here, the grouping symbol is being represented by the absolute value bar. So this is very, very generic. So although this seems overwhelming, it gets easier and easier and easier with practice. So let's dive in. There's 4 questions that we have to ask ourselves to see how this graph has been transformed. So we'll always number them 1, 2, 3, 4 off to the side. And that's what these 4 questions on your purple note card are all about. The first question they're asking is, has this graph been reflected over the x-axis? Well, here's how you tell if it's been reflected over the x-axis. You check the A value to see if it's a negative number. If the A value is negative, then baby, this graph has been reflected over the x-axis. Where's the A value at? I've highlighted him green for you right here. As you can see, here's those 4 positions. There's an A value in green, some B value, he's the number in front of x, inside the group. H value is in blue, and notice This stupid h has a minus in front of it, so we have to think opposite game with that. And this k value is in pink, being added or subtracted outside the group. So first question, has this guy been reflected over the x-axis? We got to check the a value. Well, here's our a value. It doesn't actually really have a number there. I think that we all know that if there's not a number in a multiplication situation, they're talking about the number 1. Is this guy negative? The answer is no, it is not. So they want to know, has this been reflected over the x-axis? The answer is no. So we're going to put a little dash here. Instead of just writing out the dash, we're going to put a little dash right there. Or writing out the word no, we're going to put a dash. So what does that mean? Here is what the graph started like. Remember, the parent function is Mr. Absolute Value V. Please don't sketch this, just watch me. This is what it looked like. They want to know, on this messed up dude right here, has he been reflected over the x-axis? Well, that's a no. So since this absolute value guy opens up, our final sketch is going to open up also. Now, here's the second thing that could happen. It could be translated. A translation is just a slide, like moving left and right and up and down, and it slides around. It's always translated h comma k. So let's see what this is. We'll always put a big old capital T for the translation. H is this blue number inside the group being added or subtracted. In this case, it is this +1. But because of this dang minus, we've got to do the opposite game of this. So that +1 actually means a -1. And what does that mean? That means that this thing has been translated 1 unit to the left, the negative. Remember x, let's talk about stuff that's happened with x. X is our left and right on the graph, so the h value is always shifting stuff left and right, and it's 1 unit to the left. Then this k value is what has happened to the old up and down situation. So that is, since there's a plus in front of this generic letter right here, what you see is what you get. So this has moved 7 units up. So I can tell by looking at this guy, this graph has been translated 1 unit to the left and 7 units up. So please don't sketch this, but here's what's happened so far. The vertex of that absolute value was at 0, 0. It's moved 1 unit left and 7 units up. So right now, the graph has done this. It is translated. It has slid 1 unit left and 7 units up. But that's not all that could happen. You could also do some sort of dilation. A dilation is a size change. So there's 2 different types of size changes that could happen. A vertical dilation or a horizontal dilation. So this looks complicated, and it kind of is. Hang with me on it. They want to know, has this graph had a vertical dilation at all? Well, here's how we tell. We got to look at the a value, right? The a value is 1. Remember, that's that green number right here. And then we got to take its absolute value. To see those bars right there? So we got to make him positive. So okay, we'll take 1 and we'll make him positive, and he still turns out to be 1. If that number is bigger than 1, this thing has been vertically stretched. And is 1 bigger than 1? No, it's not. So it has not been vertically stretched. They want to know if this thing has been vertically compressed. Well, we take that a value, we make him positive, and if he's between 0 and 1, that has happened. Is 1 between 0 and 1? No, it is not. So this thing has not gotten vertically stretched. So, okay, no size change there. Has it been horizontally changed? It's about that b value. The b value is the number in front of x. Well, the number in front of x is a 1. If 1 is bigger than 1, when you take its absolute value, it's been horizontally compressed. If 1 is between 0 and 1, it's been horizontally stretched. Well, 1 doesn't fit any of those categories either, so this guy hasn't changed size at all. So there has been no kind of dilation, so we'll do this. And then the last thing is they want to know if this thing has been reflected over the y-axis. How do you tell? If the b value is negative. We'll check out our b value. Our b value is 1. He is not negative, so that has not happened. So we're going to start from scratch. I'm going to erase all this, and we're going to make a sketch of what this guy looks like. First thing we got to do is figure out which way this guy opens. He looks like an absolute value v because that's his parent function. Which way does he open? Since it has not been reflected over the x-axis, he opens up. Then I got to move him 1 unit left and 7 units up. So boom, boom. And I should have asked how fat or skinny this guy is. He is normal size. And we'll talk more about that here in a second. And he has not been reflected over the x-axis or the y-axis. So we will then finally put our little vertex of 1, 7 in that spot. So this is this guy, and the last thing we'll do is write a sentence. Here's how we'll start our sentence. We'll start every single sentence to describe what has happened. Say, the graph of. The graph of. And then whoever the parent function is, we're going to list that right here. The graph of y equals absolute value of x. So every one of our sentences today starts with the graph of parent. It's not always going to be this guy. It just depends on who the parent function is. Then, out of all 4 of these, you list them in your sentence if they actually happened. If this guy's been reflected over the x-axis, you would write that down, has been reflected over the x-axis. But that didn't happen. So then we'll say translated 1 unit left. Please don't say negative 1 units left. It hasn't been moved negative 1 unit. Move 1 unit, and the negative part means left, and 7 units up. That's how this dude right here relates to the parent function. He has been translated 1 unit left and 7 units. Well, if that seemed overwhelming, that's normal. Let's try another one, right, to where we can, all right, let's get better at it. We tried one. That was weird. Let's try another one. First, we got to recognize what type of graph this is. Is he a line? Is he a parabola? Is he an absolute value guy? See the bars? The parent function is your absolute value. So parent y equals absolute value of x, which means he is a v that normally opens up. What we want to see is what has happened to this guy. So this was the vanilla ice cream. We're going to change the flavors. Let's go find in these A, B, H, and K's. If you want to highlight, you're more than welcome to highlight. I always do the A value is green personally. That is the number outside of the grouping symbol. In this case is the absolute value GARs and being multiplied by. The B value is the number right inside the group. In front of x, though, in this case is a 1. The H value is this guy being added or subtracted to x inside the group, and he's got that weird opposite game thing going on for him. And this K value is outside the group being added or subtracted. So here's A, B, H, and K. Let's see, has this guy been reflected over the x-axis? How do you tell? Well, this will tell you. If the A value is negative, A value is the green boy, yes, he is negative, so this has been reflected over the x-axis. We'll use a lowercase r to mean reflected and a little subscript of x to say it has been reflected over the x. Remember, it can be reflected over the y down here also, so that's why that's important. What does that mean? Well, the absolute value v normally opened up. Since he's been reflected over the x-axis, our sketchy poo is going to have to open down in that case. So let's do the translation now. The translation is h comma k. H is right here. It's just opposite game because of this stupid minus in front of there. So since that says a -3, we're going to have a +3, which means 3 units to the right. And then this guy has a plus in front of it, so what you see is what you get. That's going to be 7 units down. So that's not bad. Our absolute value v that opens down has now been moved 3 units to the right and 7 units down. Let's see if its size changed at all, if it's been dilated. It's all about those numbers of A and B. So first, let's check vertical. Vertical dilations are about the A value. Our A value is -1, but you see how there's bars? These absolute value bars say, hey, dude, you've got to take the absolute value of -1, and that becomes 1. So my question is 1 bigger than 1? If it was, that would mean this guy gets vertically stretched, which is skinnier. Nope, has not been vertically stretched because 1's not bigger than 1. Is 1 between 0 and 1? No, it's not. So it hasn't been vertically compressed, which means it gets fatter in that case. So no vertical dilation. Has it been horizontally dilated? How do we check? We check out our B value, which is 1, and we take the absolute value of that, which will still be 1, and see if it fits these bills. Is 1 bigger than 1? No. Is 1 between 0 and 1? No. This hasn't happened. And let's see after 2 examples if that makes sense. Dude, we took something times 1. Taking something times 1 doesn't change your size at all, right? So a dilation is a size change. If you want to take stuff times 1, it doesn't change the size. So nope, our absolute value V is normal size. He's not any fatter or skinnier than before. How about if this guy's been reflected over the y-axis? It's about this B value being negative. That B value is not negative, so boom. Let's see if we can make a nice little sketch of this guy, though. So he is an absolute value V. Thank you, parent. He's supposed to open down, right, because it's been reflected over the x-axis. And I got to move him 3 units to the right and 7 units down. And I'll put this as a nice little ordered pair here. What size should I make my V? Normal size. How do I know if you're making it normal size? Well, we'll see when we have to start making some fatter or skinnier, but it's just a little guessing game. This is a normal size, and he has not been reflected over the y-axis. If he would, we'd have to jump him over across here, and he'd be over in this zone right there. So last thing is write our sentence. We'll say the graph of parent function. In this case, the parent function is y equals absolute value of x. It's not always going to be that. We'll see that on the next problem, but the graph of parent has been, and then whatever you write in this 4 steps, it goes in the sentence in the order that we put them in also. So it has been reflected over the x-axis. It has been translated 3 units right and 7 units down, and that's the only thing that happened to it. Weird. So pause the video if you need to write that sentence, and then we're going to keep on keeping on to the next one. This guy right here, let's recognize the parent. You see there's no more absolute value bars. He's not going to be an absolute value function. This is going to be a little squared dude, which is a quadratic, which it makes a parabola. So the parent function is going to strip away all this weird stuff and go straight to y equals x squared, which as a parent function is a parabola that opens up. Let's find our 4 major players of A, B, H, and K. A is the number outside the grouping symbols, right in front. B is the number inside the grouping symbols, right in front of x, so that's this -1 right here. H is the number being added or subtracted inside the group, and look, there's nothing being added or subtracted. And K is the number outside the grouping symbols being added or subtracted to this guy. So here's A, here's B, here's H, and here's K. Let's see and answer these 4 questions. Has this parabola, which normally opens up, been reflected over the x-axis? How do I know? If this A value is negative. Is the A value negative? Nope. So no, it has not been reflected over the x-axis. That means that since this guy started opening up, our little sketchy poo is also going to open up. Where has it been translated? H comma K. H, see how they added nothing to this? This is the same thing as having like -x plus 0 on this. You know, it's not a 1 because 1's there when you're multiplying stuff. This is being added or subtracted, and you're adding nothing to it. So that has moved 0 units to the right or left, however you want to think of it. Still goes nowhere. And this 8, it has a minus in front of it. What you see is what you get. It says, hey, use the normal thing, so it's going to move 8 units down. Then translation time. Excuse me, we did translate. Let's do dilations. Let's first see if it's been vertically dilated by looking at the A value and making him positive. The A value is 1, make him positive. Cool, he's still 1. And when you take something times 1, it doesn't change your value. So boom, no vertical dilation. How about a horizontal dilation? It's about that B value, which is a -1. But we have to think of him as positive. We have to take its absolute value. An absolute value of -1 is a positive 1. So 1 doesn't change your size when you multiply by it. So there has been no dilations whatsoever. And then let's go for step 4. Step 4, has this guy been reflected over the y-axis? It's about the B value being negative. And yes, that has happened. So we'll put a little reflect over the y-axis. And now let's make our sketch. So this is our parabola. It's got to open up, and we got to move him 8 units down. So bada boom. So moving him 8 units down. Then what size should I make him? Normal, fatter, or skinnier? Well, he's a normal guy. And then reflect him over the y-axis also. Well, that's a weirdo, because the vertex is on the y-axis. When you reflect him over the y-axis, it doesn't go anywhere. So he's still just your normal parabola that's been shifted 8 units down. And yeah, he got reflected over the y-axis, but it didn't do much. So let's write our sentence. The graph of parent, here he is. Do you see how the parent function isn't the absolute value of x anymore? It's y equals x squared, has been, boom. First thing that happened is translated 8 units down. You don't have to say move to 0 units, right? That's ridiculous. So moved 8 units down and reflected over the y-axis. Even though it didn't do much to the graph, we're still going to put it because it did happen in this function. So weird. Again, pause if you need to for writing the sentences and everything. I know we don't like writing the sentences. It's a big part of college algebra, and that's what we're prepping you for. So we'll write the sentence. And let's do another one. So let's recognize the parent function. Looking through here, do you see the bars? Yep, this is an absolute value, guys. So parent y equals absolute value of x. Then let's go find our four major players of A, B, H, and K. A is the number outside the grouping symbols right here in front. B is the number inside the grouping symbols right in front of X. H is in the group being added or subtracted, and yep, it's opposite game. And K is a number outside the group. I want to highlight in pink. Outside the group being added or subtracted. So I think it's getting a little easier. Here's A, B, H, and K. Now let's see what happens. First of all, this is a V graph that normally opens up. All parent absolute value guys open up. Has this guy been reflected over the x-axis? It's about if this is negative. And he is. So it has been reflected over the x-axis. That means our sketchy poo is going to have a V opening down. But what else has happened to the V? Well, it's been translated somewhere, so we'll put the big T for translation. H, opposite game. So that's 4 units left. And K, 3 units down. What you see is what you get. How come? Because it's normal. It's got a normal plus in front of it, so -3 is the K value. So our V has been moved 4 units left and 3 units down. Let's see if he's been dilated anywhere. I'm going to check a vertical dilation. Vertical dilations are about that A value, which is a -1/2. But I have to make him positive. And oh man, the absolute value of a -1/2 is 1/2. And since it's not 1, something's going to happen. Let's see if it got vertically stretched, which means gets skinnier. If you're not sure what that's all about, see me in person. I'll show you what vertically stretched is all about. But vertically stretched, it gets skinnier, looks like this. If 1/2 is bigger than 1, that would have happened. Is 1/2 bigger than 1? Nope. So how about 1/2 being between 0 and 1? Is 1/2 between 0 and 1? Oh yeah. That means this guy gets a vertically compressed, we'll abbreviate it like so, times whatever that number was that we were dealing with. It's 1/2. Please don't put -1/2 because the negative has nothing to do with it. It's just 1/2. All the negative does is this. It reflects you over the x-axis. So it's been vertically compressed by 1/2. That means it's going to get fatter. Again, if you had a wet lump of clay and you vertically compress it, it's going to get fatter in that case. And let's see if this guy finally has been like, we haven't checked horizontal. Has it been horizontally dilated? Well, let's check the B value. The B value is a -1. But remember, we got to take its absolute value. So it's really a 1. And 1 doesn't change your size, dude. When you take something times 1, you stay the same. So it has not been horizontally dilated. How about reflected over the y-axis? It's if that B value is negative. Yes, sir, Bob. It is negative. So this guy is reflected over the y-axis. This will now help us make a sketch of this dude. First of all, he is a V that opens down. I just got to know that I got to make him open down. Where am I moving him to? 4 units left, because the vertex does start at 0, 0. 4 units left and 3 units down. So boom, boom, boom. -4, -3. What size will he be? He will be fatter than normal. So we'll do that in a second. But do you see how there's this weird dude at the last step that's going to reflect you over the y-axis? I'm not going to make this V yet because I know it's not going to end up being there. The whole thing is going to jump over the old y-axis. So I'm just going to move its vertex. And it's going to go roughly there. And since this was at -4, -3, this will now be at +4, -3. Just the x value change. Right? If you went 4 units left, you have to go 4 units to the right, but it's still 3 units down. And then he is a V, and then if it was a normal guy, it would be like we'd make him normal, but he's supposed to be fatter than normal, so I'm just going to give me one of these. That's what we'll do. If your normal dude looked like this, then make your other guy fatter than that. So weird. All right, let's write that sentence. The graph of parent has been, and look at this. Yep, all of it goes in the sentence. in the order that we did it. Reflected over the x-axis, translated 4 units left and 3 units down, vertically compressed by a factor of 1/2. If you just want to say times 1/2, that's totally fine. And reflected over the y-axis. You must put these in the order that we wrote them in, otherwise it doesn't end up working out right. Like if you say reflected over the x-axis and y-axis, it's like, that's not right, because it happens in this order. So we'll put that in that order. Cool. So, man, we've done a few of them. If you have some more questions, let us know, because I don't like this one anymore. I want to skip it. So we're going to skip over this guy right here, and we're going to jump to the real meat and potatoes, the multiple choice question. After doing 3 or 4 examples, let's see how using this purple note card concept can answer this multiple choice question. Bing, bang, boom, lickety-split. First, by graph recognition. See this? This is a parabola, which means it ain't you, dude, and it ain't you. Those are absolute value graphs, not going to be those. It's got to be down to A or B. With a little bit of basic purple note card, it's like, it's about which way this guy opens. Which way should this guy open, up or down, since this dude is negative? Well, that's got to be this dude. So that is choice B in this case. So that right there, even though I know you could punch that in your graphing calculator and see what the graph looks like, that takes time. It takes time to punch that in. And on the ACT, which is a timed test, the more time you can save, the better. So that took me like 5 seconds to figure out, when it would have taken me a little bit longer by punching it in my calculator. And of course, I could make a typo punching it in my calculator also. So cool. And then finally, they give us the sentence. We got to go and make the equation. Here's what they do. They do a bad thing. They don't put stuff in the right order. They write the sentence out of order. What is wrong? But they're just trying to trick us. So here's what we got to do. We got to kind of read through this for a general and find the parent function. This is the parent function. And here's how I start. I write it like this, where I've got the parentheses being squared, and I got an X in there, but I give myself space for these guys. See the A, B, H, and K, like how I've been highlighting them all day? You know, it's like, yeah, I'm going to leave myself space. Now, you don't have to highlight them, but I just want you to see, here's where an A value goes, a B value, an H value, and a K value. We're going to read through this sentence and figure out who we're putting where. So the graph of y equals x squared has been translated 3 units to the left. So a translation to the left is about this blue dude. That's your left and right, McGee. I'm going to put a 3 in there. And we all know that to the left means negative. But don't forget, this is opposite game right here. So you actually have to have the positive, right? To go left, you need the opposite game right here. He's a weirdo. 4 units up. Cool. That's a 4 right here, but don't forget, this is what you see is what you get, so since you want to go up, you will put the plus. Reflected over the x-axis, so the reflection over the x-axis stuff is all about the green thing, that A value. He's going to be negative. Vertically stretched, I don't care if it's vertically stretched or vertically compressed, all vertical dilations are about the A value, so we'll put that 7 right here. And that took care of all of it. They didn't end up doing anything with this B value, so we'll just leave that spot empty in that case. And there's your final. So the old transformations of graphs, it'll be a real handy thing. It's not going away. We're going to do it all year long, so it's a cool thing. If you have questions, please come see us, and we are happy to help. Have a good one.